Welcome back. In this concept development page, we're going to be talking about vectors, and vectors, remember, are forces that are acting in one direction or another. So a vector is anything that has magnitude and a direction. So a force, say, of weight is going to be acting towards the center of the earth because your weight is pulled. And in this case, Nellie Newton is hanging from strings. And so since she's hanging from strings and the string hasn't broken, you've got a tension in that string. And that tension in the string is equal to her force. Now, if you were doing this geometrically, you've got a length of an arrow. The length of an arrow corresponds to the strength of that force. So for instance, if she weighed more, we would make the arrow longer. And since she had whatever her weight is equal to the tension on the string, we're going to say that those are equal forces. Okay, so this vector is equal to this vector, and she's static. So she's staying put. She doesn't move because the vectors are balanced. Anytime that you have two forces that are acting opposed to each other, they cancel each other out. So if this, for instance, was a force was larger than this force, she would actually go up. If the force is acting down is larger than the one that's acting up, she'll fall down. Okay, so since she's not moving, these forces are exactly equal. Now in the second example, this is the same force of her weight. She weighs the same, so we're going to have a certain length of a force to show you this, but she is holding herself on two strings. So the weight of the tension in this string is not the same as the tension on the first. In fact, since she's on two strings, we're going to say that the tension is half what the tension was, because half of her weight is suspended with her left hand, half of her weight is suspended on her right hand. So we're going to make this half of what it was before. So I've got a somewhat of about a half of an inch. Okay, so or about 3/4 of an inch. So I'm going to make it half of that amount acting up, and there's two forces half as much as the original force. So when you add those forces together, you've got two short ones that equal in length to the long one, and two are acting up, one is acting down, and she's still static. She's not moving, she's not falling down, and she's not being hoisted up. Okay? You could imagine if those cords were attached to a helicopter, she could be hoisted up from the ground, but these forces would be much higher than the force of her weight. Okay? So here's a cool one. What if the strings are not equal? Is she moving? That's the question you're asking. Is she static or is she moving? If she's moving, then the forces are not balanced. If she is static, then they are balanced. So we've got this force is acting here. Could you imagine a scenario where she could be hanging from a tilted beam and still not be moving? And the answer is yes, she could. It doesn't matter that this string is short. One half of that length, half of this length is equal in here, and the other one would be here. So these two would be the same distance as this, and it doesn't necessarily matter that it's bent or not bent. So we see here she's hanging from a tree. It's bent. What's going to happen here? What would you say? You have the same weight, the same force vector acting down. This is her weight. Okay, it's her mass times whatever the pull of gravity is weight. And then what about the tension in the line? Is all the tension going to be in each line? Nope, it wasn't here where she was suspended with 2 ropes. Now she's suspended by 3 ropes, and so you're going to get 1/3 of the amount is in each of the cords. Okay, 1/3 of the tension of her weight is in this cord, 1/3 in this cord, 1/3 in this cord. So the more cords that are holding you up, the less tension is in each cord, and the stronger the cord is. That's why for like a bridge, you would take thousands of wires and twist them together and make a cord out of the wire. So each cord is independently holding something, and eventually it has enough strength to hold up a bridge. Okay, so here's the last part. circle the correct answer. We see that tension in a rope is dependent or independent on the length of the rope. Okay, so we had really long ropes here. We have a short rope and a long rope here. Was the tension in the rope dependent upon how long the rope was? What does your table say? We see here that these are equal. This is going to be 1/2 of her vector weight. This is 1/2, and it's the same here. So this didn't depend upon whether this was long and this was short, and this didn't depend on whether this was long and this was short and this was in the middle. This is simply 1/3 of her weight. This is 1/2 of her weight. So this is independent of the length of the rope. Okay, so the length of the rope doesn't matter. You can have a very tight rope that's short, and you can have a very tight rope that's long. It depends on the force. So the length of the vector representing the rope tension, okay, that's what this is. The length of the vector representing the tension on the rope is it dependent or independent on how long that the rope is? Okay, what does your table say? Okay. If the tension of the rope is independent, okay, then the vector length, which represents that tension, is also independent. All right? This was nice and short. I hope you did well. Thank you.